All right, so I am okay. So open. So in today's session, I will for the next 30 minutes. Hopefully, I know how long I will be able to put this, but yeah, if it's not completed today, then I will. Okay, so today I'm going to read this paper. It is like seminar paper, which is Google file system. I'm sure if you ever heard of it, but if you haven't, then yeah, welcome. Uh, it's not. It is my first time reading the paper, but like I've read summary of this paper like time ago. Just the summary actually. I wasn't really interested in the details, but now like I actually want to um, try to read the paper from start to finish. Right. So here I have actually tablet here. Um. So yeah. So let's start first. Okay, we have designed and implemented Google file system. Okay, sorry. This is quite old actually, from 2002, 2003. Okay, we designed and implemented Google file system scalable. This file system for large distributed data intensive application. It provides fault tolerance while running on expensive hardware, and it delivers high, high aggregate performance to a large number of clients, while sharing many of the same goals as a previous distributed system. I don't know what it refers as previous distributed file system, but yeah, let's move on. Our design has been driven by observation of our application for and logical environment for current and anticipated that reflect a marked departure from earlier file system assumption. Yet we have no idea what it is, but let's move on. This has led us to traditional choices and for radically different design point. Okay. File system successfully met our storage need, widely adopted within Google as a storage platform. I don't know if it's actually still being used, but like I was thinking this is the base of the object. Probably not. Probably not. Yeah. Okay. Process generation and processing data by our service, as well as research and development that require large data set. The large cluster, the date provides hundreds of terabytes of storage across thousands of on over thousands of machines. This can currently accessed by hundreds of clients. Hundreds of clients is quite useful to expect like 100,000, but this is it. In this paper, we present file system interface extension designed to support distributed application, because many aspects of design and report measurement for micro benchmark and reward choose. It is about the previous file system refers to. Okay, introduction. We have designed and implemented GFS to meet the rapidly growing Google data processing need. GFS shares many of the same previous distributed file systems, such as performance, scalability, and availability. However, its design has been driven by this first component failure. Okay, this is the design choice are the norm rather than an exception. The file system consists of hundreds of even thousands of storage machines built from inexpensive company ports and is accessed by a comparable number of client machines. The quantity and the quality of components virtually guarantee that some are not functional at any given time, and some will not recover from their current failure. Fair enough. We have seen some problems caused by application bugs, operating system bugs, human error, and the failures of this memory connector, networking, power supply, blah blah. Common problem in this process. Therefore, constant monitoring and collection for variance must be installed to the system. Second, files are huge by traditional time. multi-gigabyte files are common. Each file typically contains many application objects such as web document. When we are regularly working with fast-growing datasets of many terabytes comprising billions of objects, it is unlikely to manage billions of approximately kilobyte-sized files, even when the file system could support it. As a result, design assumptions and parameters such as I/O operation and block sizes have to be revisited. Third, most files are mutated by appending new data rather than overwriting the existing data. So it's like no in-place update. Random writes within a file are practically non-existent. So there's no random I/O. This is all append only. And once written, the files are only read and often sequentially. Priority of data. Here this characteristic. Some may constitute a large repository that data analysis programs can through. Some may data stream continuously by running an application archival of the data. Some may be intermediate result produced in one machine and proceed to other, whether simultaneously or later in time. Given this access pattern on huge files, appending becomes the focus of performance optimization and automatic guarantee, while caching data blocks, the client loses its appeal. Okay, so no caching, it's on append only. While data fourth, okay, for co-designing the application and the file system API benefits the overall system by increasing what is co-designing? The application file system. So the application and the file system API. It's like, if I remember correctly, this is like client. The server is actually like not completely not completely transparent, not completely unknowingly server. Like the client has awareness of where the server is and what has been done and blah blah blah. So like clients like stateful in some sense. For example, we have relaxed the GFS consistency model to vastly simplify the file system without imposing an onerous burden on the application. What is application? We have also introduced an atomic append so that multiple clients can append concurrently to a file without extra synchronization. Okay, that's pretty cool. Like normally if you append something together like concurrently, then you expect that to be like, I don't know, overrode each other. Overrode each other. Okay, so this one is, yeah, super cool. Where's it? Okay, this will discuss more detail later. Right, so multiple GFS clusters are currently deployed for different purposes. The largest one have over 100 storage nodes, over 300 terabytes of disk storage, and heavily accessed by hundreds of clients on distinct machine on a continuous basis. Okay, this is an overview. Actually, in designing file system for our need, we have guided by assumption that offer both challenges and opportunities. We alluded some key persuasion and no layout or assumption in more detail. Okay, the system is built from many inexpensive commodity. Okay, this one, the first one, often fails. So it must be constantly monitor itself, detect and tolerate recover promptly from component failure on daily. Recover promptly on daily basis. Basically, like it has to be replaced. It has to be hot swappable, and so your system should be able to do that. The system stores a modest number of large file, so it focuses on large file. Like it's not really focused on like small files. Expect a few millions file. It's typically 100 megabytes or large in size. Multi-gigabytes are the common case and should be efficient. Small file, well, it is must be supported, but we it not optimized for. So I know that even in like any distributed dot system like S3 for example, if you are using S3 and you are doing like a lot of small files, right? It's like going to cost you a fortune because it is not really optimized for that. Yeah, I mean it's not really smart if you're using S3 and try to module your write and read operation as like small micro writes instead of like trying to patch everything together and to put it into put requests. So yeah, this is the same thing. Uh, the workloads primarily consist of two kinds: reads, reads. Okay, the reads is large streaming read, and small random reads. In a large streaming read, individual operations typically read hundreds of kilobytes, more commonly 1 terabyte or more. So this is like the block size, the minimum read. No, I mean not the minimum read, but like the typical read. Okay, yeah. Successive operation from the same client often read through contiguous region file. So yeah, so it is not, it is sequential read. Sequential read. So you go one channel after the other. And okay, a small random read typically reads a few kilobytes at some arbitrary offset. So you are randomly read the port, and you read this port, read somewhere port here. All right, so performance conscious applications often batch and sort their small reads to advance steadily with it. Batch their small read to advance steadily rather to the okay, so you are technically can do, hey, I want to read this offset, this offset, this offset, this offset, this offset. Okay, give me offset. Like instead of going back and forth. Which is like, I think behind the scene it should be like doing the same, but like yeah, batch operation is always performance efficient than oh, then you know you're doing it one by one. That's quite obvious, but it's such a nice API. If your software support this kind of thing, well, this batch operation it's always nice rather than doing it on client side, which is client side, which is like you know it's such a burden for the client. So like a good design. The workload also have many large sequential writes that append data to files. Okay, typical operation sizes are similar for those to those for reads. Okay, so some workload have large sequential writes, and then also large sequential read. This one is like this is the primary. This is other workload types. Uh, Once written, files are seldom modified again. Okay, so this is the big file modified, not even appending to it, right? Small writes at arbitrary position in the file are spotted, but do not have to be efficient. So you have this block of file like this. You want to write in the middle of it. Technically, you can do that, but you know, behind the scene it might have to I don't know, doesn't have to be efficient. It's like it seems like you know, maybe you have to rewrite this entire thing, moving it somewhere else. Oh, sorry. Yeah, what's that? This is the front and this is the back. You want to read from here. You want to append from here. Maybe you have to relocate the rest of this somewhere. So this is it might no it doesn't have to be this. I mean like this is just what it mean by it doesn't have to, it doesn't have to be efficient. It doesn't have to be efficient. So yeah. Okay, next, system must efficiently implement well-defined semantic. for multiple clients that concurrently append to the same file. Okay, so files are often used as producer or file transfer or many way merging. Okay, this is actually complicated things. Hundreds of producers running one per machine will concurrently append to a file. Atomicity with the minimal synchronization overhead is essential. The file may be read later, or the consumer may be reading through the files immediately. So while the producer are writing the file, the consumer may be reading simultaneously. Okay, so it's like streaming in some sense. Someone write it, someone read it. That high sustained bandwidth is more important than low latency. Yeah, bandwidth and latency. So you can write big chunks of file at once is better than you can you have to like write it. You have to respond in super fast manner, like low latency. Latency versus bandwidth. So people often quite like misinterpreted. So yeah, most of our target application place a premium on processing data input at high rate, while a few have stringent response time for an individual read. Okay, so this is the first priority. This second, you have stringent response. So individual read and write, you can do it fast enough, but it's not a priority. Yeah, this is the interesting thing about this. Like, okay, we have all of this thing. They sadly know that what they want and they do not want, or they do not want to optimize. Then this is like very nice. I know, like in the real organization, this kind of thing is like hard to define. Like, no, okay. Let's talk about that later. Okay, so interface. CFS provides a similar file system interface through, though it does not implement a standard API such as POSIX. Okay, so it doesn't have to like read, write, write. Files are organized hierarchically in directories ended by add names. We support the usual operation to create, delete. Okay, so this is standard. This is the subset of POSIX. So POSIX is much more than this, but like they do not implement everything. Moreover, GVS has a snapshot and record append operation. So this is not POSIX stuff. Snapshot creates a copy of a file or a directory at low cost. How did they do that? Record append allows multiple clients to append data to the same file concurrently while guaranteeing the atomicity of each individual client's append. Wow. You mentioned it 3 times. It is useful for implementing multi-way merge sort and producer consumer queues that have that many clients can simultaneously send to without locking. We have found these types of files to be infallible in building large distributed application. Snapshot and record append or cause further in the section 4. 3.4 and 3.3. Okay, there's still a long way to go. Okay, GFS cluster consists of a single master. Okay, this is single master and multiple chunk servers. So this is, what's it? Is it like single point of failure? So the master dies. I don't know. The server dies. I don't know. Okay, multiple chunk server. All right, and it's accessed by multiple clients shown in figure 1. Where's figure 1? Okay, let's take a look at it later. Okay, each of this, what is the client? commodity Linux machine running a user level server process. It is easy to run both a server and a client on the same machine. Why? Wait, the client is the one that writes the server, right? Is it the kind of give us client master chunk server? Okay, you okay. I think what you mean is that you want to highlight that it is easy to run chunk server and client on the same machine, but you don't have to do that. And the lower reliability caused by running possibly flaky application code is such. Yeah, I mean, I don't know why I even have to mention that. I mean, yeah, you can run your server on your own machine and call the server, like that's going to be fast, but like why? This is large distributed system. Why would you want to run the application on the same server, the same machine as the server? Okay. Anyway, files are divided into fixed chunks. Okay, this is start getting more technical. Each chunk is identified by an immutable and globally unique 64-bit chunk handle, like chunk ID, assigned by the master at the time of chunk creation. Okay, so the master has to be like a really big machine, otherwise that it will choke the entire system, because like everything has to be assigned by the master. I know that it could possibly a super chip operation. I don't know, it could be like UUID or something, but you know it's still no centralized. Like uh yeah, yeah, that's their decision. It's easier to do this, to be honest. But, yeah. And chunk server creation. Okay, chunk server stores stored chunks on local disk as Linux files and read or write chunk data specified by a chunk handle and byte range. Read or write data specified by chunk handle and the byte and byte range. I don't understand. Okay, let's just move on. Variability. Uh, um, Variability. Each chunk is okay. Chunk is replicated on a multiple chunk server. Replicated to multiple chunk server. Okay, that makes sense. Makes sense. Yeah, replicated multiple chunks. That makes sense. Yeah, multiple chunks. By default, we store 3 replicas. The user can designate different replication level for different region of the file space. That makes sense. But the more replica you need, the slower it gets, because every time you write something, then you have to wait for the entire uh, replica to convert to confirm that they have written the file. The master maintains all file system metadata. See, this is like yeah, another point of failure that you mentioned this kind of thing like today, like they're going to be, oh man, that's like single point of failure. Like, oh, if the master dies, then all the system metadata gone. Your file's going to be basically useless because you cannot read them back. Right? Yeah, that's I don't know. This includes namespace, access control information, the mapping from files to chunk, the mapping. Look at this: namespace, access control information, mapping from files to chunk. Look at this. This is the most important. Basically, like, okay, this file broken into a few chunks, and like, if I want to get like this byte range, I have to go to this chunk server. And like, if I lose the information, basically that chunk at this random chunk server become useless. Like, I cannot retrieve it back. It's just arbitrary bytes, unless each of these chunk have their like metadata header of okay, who owned this, like when this is written, and where is the rest of my friends. But that's going to be a huge metadata overhead, which I think they are not going to do it. So they like put really high trust in the master. Yeah. Uh, right. So the current location of the chunk. What was this? Oh, it's like DNS. I don't know. It also controls system-wide activities such as chunk lease management, the collection of or parent chunk. This is what I mean. Like, okay, if the metadata doesn't exist in the chunk, sorry, in the master anymore, then that means every chunk, every random chunks that just gone, like they just like become garbage and they have to be collected. This is why I have garbage collection. The chunk migration between chunk servers. So this is like balancing, it's like the Elasticsearch. No, it's like basically every disposition do this kind of balancing, right? So the master theoretically communicates with each chunk server in a heartbeat. Normal message to give it the instruction and collect state. I don't know, does it apply some kind of consensus application? Because service like I know, I don't think so, because there's only one master. I don't think it needs consensus. CFS client could link into each application, implements the file system API, and communicates with the master and chunk server to read or write data on behalf of the application. Okay, so the client has to be like something stateful. It understand the API and stuff. So it's not like REST API. It does have a state, right? Client interact with master for metadata operation. I don't understand, like, and client server. I mean, I don't understand this part. I know, like, you write or read on behalf of application, of course. Like, who else you want to write or read on behalf of who? If it's not for the application. Okay, I don't know, but yeah. But all data during communication goes directly to chunk server. So yeah, the master is just like metadata server. It doesn't have direct data, but yeah, everything. It just basically points out, hey, you client, if you want to read this part, go to that, go to that, go to there, go to that chunk server, go to the chunk server. We do not provide POSIX API and therefore do not need to therefore need not hook into the Linux Unit server. To be honest, I have no idea what is Linux Unit layer. I think it's like mount, so it's not mountable in some way. So you don't have an abstraction of POSIX API that makes this file system become mountable on client system. Is that what you mean? Probably. Okay. Oh, okay. So let's complete this and like let's break. Neither the client nor the chunk server has file data. Wait, has the file data. Wait, but the chunk server contains the file data. Client caches. Okay, the client is okay. I understand it, but the chunk server is literally store the data. Why would you? Why would you even mention that you need to that the chunk server does not has the data? I mean, it doesn't have to. Client cache over little benefit because most applications stream through huge file or not working or have working sets too large to be cached. Okay, that makes sense. Not having them simplifies the client and the overall system by eliminating cache coherent issue. Yeah, caching is hard. Client do cache method, however, yeah, it is just like probably this chance file go to this chance server. So it's like DNS in some way. You don't know, every machine that needs to query DNS once in a while, and then like they expire it after a while to requiring the DNS. Same concept, I believe. Chunk servers need not case file data because chunks are stored as local file. Yeah, that's exactly what I mean. Like, you don't have to mention this. I don't know. Okay, this is clear. As local files, so Linux buffer cache already implement already keeps frequently executed in memory. Right. Okay, so this is the application, of course, file chunks index. If it's master, file name space, Cooper, okay, chunk. Okay, chunk this, go to here. Data message, yeah. This is control. This is control plane, and this is data plane. Like, yeah. This is store the data. And this is actually like local file system. Yeah, I mean like this is local. It does not like store the file somewhere else. It's there. Okay, I think it's 4:30. I will post streaming and like continue later. See you.